welcome to our fifth webinar of the spring for the USACM Energy and Earth Systems Technical Thrust Area. So I'm the chair of the TTA. I'm Irina Tazauer. Just to tell you a little bit about the TTA, so we're a part of the U.S. Association for Computational Mechanics, and we cover a variety of topics, including some of the ones listed here. So climate and earth system modeling, climate coupling, geomechanics, wind, solar, nuclear energy, carbon sequestration, capture, storage, oil, gas recovery, and some others as well. And so I would encourage you to join the TTA. So if you're a part of the USACM, joining is free. If you don't want to pay, you can still kind of keep up with what we're doing by following our LinkedIn page, where I post updates on activities, including these webinars. So the other announcement I wanted to make, there is an election going on right now for the TTA for two new members at large, and it's kind of a weird name, but there's a chair, a vice chair, and then the two members at large that comprise the leadership committee of the technical thrust area. So there's three candidates right now. So it's myself, Professor Anjali Sandeep from University of North Dakota, and Professor Eirik Valseth from the Norwegian University of Life Sciences. So actually tomorrow is the last day to vote. So if you haven't voted, please do so. I think if you don't have the ballot, you can email me and I can figure out how to get it to you, but those were emailed out earlier. And we already have a new chair and a new vice chair. So the new chair starting, I think, midsummer, early fall is Professor Ravi Thaidu from Vanderbilt, and the next vice chair will be Professor Hannah Liu from UT Austin. So in terms of the webinar series, we're almost at the end here. So this is our fifth webinar. We do have one more. It got a little bit rescheduled, but now it's kind of more evenly spaced with the others. So the next one will be June 23rd by Dr. Shamina Hossain McKenzie from Sandia National Labs, who will be talking about some of her electric grid work. And then after that, we'll have a pause for the summer, and that will be my last webinar, actually, because the new officers will take over after that. So with that, let me introduce our speaker for today. And Libby, maybe you can go ahead and start sharing the slides. So the speaker today is Professor Libby Barnes from Boston University. She is a climate scientist and professor of computing and data sciences and earth and environment at Boston University, where she also leads research in the intersection of climate science and artificial intelligence. Her work focuses on understanding Earth system variability, predictability, and change across timescales, with a particular emphasis on developing interpretable, scientifically grounded machine learning methods to improve environmental forecasting and inform human Earth system futures. She is a fellow of the American Geophysical Union and the American Meteorological Society, and she has also received numerous honors, including the PCASE Award, the Presidential Early Career Award for Scientists and Engineers, and the AGU Massel-Wayne Award, medal. So with that, I'll go ahead and hand it over to Libby. She's going to be talking about explainable AI for Earth system prediction.
Great, thank you, and thank you for everybody for being here. And just a note, I mentioned this to Irina, but there could be a fire alarm in my building, so let's hope they stay on schedule and don't start it early. Okay, so I'm going to talk about some work we're doing here in our group. As Irina already said in the intro, I'm thinking about explainable AI for system prediction. So using AI, but not just as a black box, but trying to learn something from it as well. So just to be clear, AI for weather and climate has arrived. We've had it now for multiple years, really seeing exciting advances in this space. So just as an example, this is a video from NVIDIA. On the left is an AI model. On the right is ground truth, in this case, Era 5. And if you squint and just look, or if you just look at it, it looks beautiful. Of course, it's the details that really matter for forecasting and simulating the physics of the Earth system. And in fact, they have improved dramatically over just a few years. So just in the last few years, seeing skill that is now on par with our best weather forecasting models to date. In this case, the comparing often to the IFS, so ECMWF's model. And some would argue that the AI models have surpassed that skill, and others have argued that they can't because they're using similar data with ERA 5, but either way, they're of comparable skill. And so now, there are lots of uses for AI. One of them that it is relatively inexpensive compared to many of our other large ensemble generating weather and climate models. And so we can run thousands of simulations, enough, to capture the rarest events. And I think this is, for me as a scientist, is one of the most exciting parts of AI. So again, AI for weather and climate is here, but I would argue that new scientific insight is lag behind. So my group has always said we're using AI not just to do things faster and better, but also to try to learn something new. And I think that learn something new, many people want to use AI for that, but the question is, how much are we actually able to do that? And I think we're in still early stages of figuring out how to learn new science and trust AI, or should, gauge our trust in AI for whether the things that it's learning are new physics or, hallucinations. So in my group, we're generally asking questions about AI, using AI-based prediction, emulation, and interpretation in support of Earth system prediction across time and space, asking, when, where, and how are environmental conditions predictable. And to really get us going, I just want to acknowledge that this is very much a group effort. So here are the many smiling faces of postdocs, research scientists, graduate students, and undergraduates in my group. And I will continue to highlight their contributions throughout this talk. So I'm going to split the talk into two parts. The first, looking at slightly older work, so a year or two older, thinking about explainable AI for climate prediction across timescales. And then second, focusing really on the recent work we're doing, even in the last few months, on using new AI emulators and designing new types of experiments to try and learn new science. So first, the more general explainability work for climate. This work has been out for a year or two. So we're thinking about trying to understand when the climate system will hit certain critical warming thresholds. So this is a plot from the most recent IPCC report, and they talk about these different warming thresholds of 1.5, 2, or 3 degrees above some pre-industrial level. There's nothing necessarily important about these exact anomalies, temperature anomalies, but they are very useful for communication and explaining the impacts in the future due to climate change. And one of the big important questions is, when might we hit these different thresholds? And in the IPCC report, there were, if you will, question marks below stating, when will this happen? One of the reasons this is complicated is if you look over 3 different climate change scenarios, so the 3 different panels, and you look at the different colored lines, each of those is a different climate model simulation. And so even though they're being forced with the same, the same scenarios, the same climate scenarios, we can get different answers for when we'll hit those different thresholds, not just from one emission scenario to the other, or socioeconomic pathway, but also within the same SSP. The climate models themselves can differ by up to 40 or 50 years for when one of these thresholds is met. Now, there are many approaches and discussions on how to deal with this type of uncertainty and whether there are some models that are better than others, etc. But in our work, we decided to use machine learning, or specifically neural networks, to try to take this information and constrain it a bit better. Specifically, what we did is we took every year, we made an annual mean map of surface temperature from each of these climate models, from each of their realizations or their ensemble members. So imagine the year you were born. We can take that year's annual mean temperature map, and we put it into a neural network. Again, this is trained on climate model data, not observations. We put it into a neural network, and we have it predict how many years in that world, in that climate model, until we reach a certain warming threshold. Now, again, because we're not training on climate models, but we're training on, because we're training on climate models, we know the right answer because we've already run these simulations forward, and we know when those models will hit these warming thresholds. Now, actually, we don't do a deterministic prediction. We don't actually have it predict the exact number of years. Instead, we have it predict the parameters of a conditional distribution, so we can actually get some uncertainty related to this prediction. And the results, the network does a good job at making this prediction. That is, when you plot the true number of years, that is the target, against the predicted number of years, you get data that falls largely along the one-to-one line, whether you're looking at the training, the validation, or the testing, withheld testing set. So the point is the network is able to learn to predict how many years until a warming threshold is reached, given this annual mean map from a suite of CMIP climate models. All right. This is not the main result, because at the end of the day, we already know this answer. It's very easy to compute if you have the data. The question is, what about the real world? How many years do we have in the present world, that the actual Earth that we live in? The point here is that we've trained this network to take in maps of temperature across the globe. And so now we can put those maps from reanalysis or from observations into our network and say, how many years now do you think we have until these thresholds are reached? So here are 4 maps of observed surface temperature from 1980, 92, 2016, 2021. And we're going to put those into our network. And when we do that, we can do that for every year that we have this data, and we can make a plot of how many years the network thinks until we reach the 2 degrees threshold. And we can plot all of those in a time series like this. And a few things we're looking for in order to gauge trust in this network. The first is, if this network were perfect, then every year we got closer, or every year we move forward in time, we would get 1 year closer to reaching that threshold. And so we're looking for a slope of -1 years per year. Now, it turns out over the last few decades, this is in fact the slope we get. I don't think, not everything is exactly -1. This just happened to be. And in fact, you might wonder why we don't go back any further, and you'll see it's because there are some strange ups and downs or wiggles in this time series. And actually, this particular bump here is from Pinatubo. I don't actually see this as necessarily an error of our network, because when Pinatubo erupted, which was not predictable, it released a bunch of aerosol, right, and debris into the stratosphere and actually cooled the Earth for the next few years. This cooling then sort of fooled the network into thinking we were further from hitting that threshold, until the effects of the volcanic eruption went away and we were back on track to this -1 years per year. So for me, I actually see this as further verification that the network is doing what I expect it to be doing. Okay, so after doing all this work, we can actually start to make PDFs of the predicted number of years we have in the real world until we hit certain thresholds, in this case 2 degrees, under a variety of SSPs. Now, again, there are other methods for doing this. This is just one, but the bottom line here for our work is that we found a higher likelihood of reaching 2 degrees in the low scenario than some previous assessments. So this was for the global map, how many years until the whole world reaches these certain thresholds. But we had a follow-up paper where we actually looked specifically at different regions. So we did this approach for all of the IPCC regions. And if we followed the approach that I just showed you, we'd be training on climate model data and then hoping it worked and predicting on observations. But in this regional work, we actually went a step further. And what we did is we trained on climate model data as before, but then we fine-tuned that model with the limited observations we had at each region for specific thresholds we have already reached. Now, again, we can't train purely on observations because we have too short of a data record, but we can use the reanalysis to do some fine-tuning. Once we fine-tune the model, then we use it to predict the observations. And when we do this, just as an example, this is for that CNA, Central North America region, we can see our base network in the teal line, which largely follows sort of the middle of all those CMIP ensemble members plotted in gray, is slightly biased towards later. So hitting these thresholds later in the time series, but by fine-tuning on just a few limited observations, just 3 different observed thresholds, we're able to actually improve that prediction overall, shifting it earlier and giving us potentially a more constrained prediction for the real world. Now, we've done this for many, many regions, and you can go to the paper if you want to look at all of these. But But overall, the takeaway was that our approach with fine-tuning significantly constrained projections, that is, made them narrower than if you'd use all of the CMIP ensemble members equally, and suggested that these thresholds will occur sooner than anticipated. All right, so we're making all these predictions, but I said the talk was titled Explainable AI. Where's the explainability? Well, you might be left wondering how, from just these maps of annual mean surface temperature, are the networks predicting the number of years we have? Is it just using the mean? What patterns is it looking for? So how did the network make its predictions? So the question we asked is, what if we could learn which regions of the globe were most relevant for, in this case, potentially improving the prediction further with observations? So there are many, many papers now on this idea of opening the black box or looking at explainable AI. Here's just a smattering of them written specifically for the earth science community. There are many methods. I like to highlight one because it really jives with how a climate scientist or an earth system scientist thinks. These are called attribution heat maps. And I'll explain what they are via example here. So imagine you've trained a network to predict the probability of a cat being in the image. So here's a picture, and there's the cat. And let's say the network outputs the probability is 0.8. What many of these attribution methods do is they will propagate that 0.8 backwards through the network, ultimately producing a heat map of the most relevant regions for that 0.8 prediction. And certain attribution methods are actually conservative in that if you add up all of the heat map values in that final attribution map, you will get 0.8. All right, so in this case, what have we learned from the attribution heat map? We've learned that the network is looking where there is a cat to determine the probability there is a cat in the image. That makes sense. But for climate, this becomes a bit more interesting. And you might be able to see where I'm going with this in a second. But first, before we get there, why should you care about XAI? As a scientist, my ultimate goal is to understand why. But I've had multiple interactions with many downstream users who really say they don't care about why. But I argue they still should care about explainable AI. So I've already mentioned this, but XAI helps us gauge trust in our networks by understanding how they are making their decisions. They also help us fine-tune and optimize. For example, if we find the network is using information that we don't think it should be, we might be able to update our network accordingly or our training practice accordingly. And finally, if the network is learning real things, we could end up probing it with these explainability methods to learn something new about the system that it has already learned. I like to point out also that the ultimate goal is to understand causality. That is, as scientists, our goal. And XAI does not give us causality, but I do believe it's a step in the right direction. All right, so let's return to our question here. We've trained networks to predict how many years until certain thresholds are met, and then we fine-tune on observations. Now I could show you many plots, but I'm going to focus on the ones that the XAI heat maps that help us understand this, if you will, bias correction via the fine-tuning. That is, we can look at the difference in these heat maps to determine what changed, what updated in the network from that base teal network to that fine-tuned orange network in that line. And this is the heat map that we get. That is, this tells us which regions were most relevant for improving upon those climate model biases when we fine-tuned on observations. And in fact, many of these regions are known regions of importance for climate change signals, including the Southern Ocean, regions off the coast of Southern Africa, as well as things like the Tibetan Plateau. All right, so going further and now moving to prediction. When we think about climate prediction, many times people think about what we call the forced response, or the fact that the climate is warming with CO2. And this is in fact the case. So if you take, we know this, but if it's nicely displayed here. So if you take a climate model and you run it, say 100 times, and all you tweak is those 1850 initial conditions. So we start the model in exactly the same place with exactly the same code. So same initial conditions, except we tweak those initial conditions by adding or subtracting, if you will, 10 to the minus 14 Kelvin anomalies. So tiny, 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 tiny differences. And you run these simulations forward in time, and in the next 100, 200 years, they end up developing very different climate variability and different trajectories. And this shows those trends that you can get from those 100 realizations from 2021 to 2050. So the main point here is they're all mostly red, which is just saying even though they are on different climate trajectories, the climate is warming in all of them. However, if you just look at trends over a shorter period of time, so instead of 30 years, let's look at 10-year trends. So 2021 to 2030, you get quite a different picture. That is, in some of these simulations, the Western US is actually cooling over these 10 years. Now, this has nothing to do with climate change. This has nothing to do with the forced response. This is in what we call internal variability, confounding our knowledge of what the future holds. Put another way, it's really a signal to noise problem where the signal in this case is much smaller than the noise. You can look at it a different way. So you can look at a single point on the map. So in this case, this is a region over Chicago. And you can look at these 100 different trajectories or simulations. And when we take the average, we call this the forced response. This is often what people are thinking about when they think about climate change and the causes of climate, what climate change causes. However, if you look at one of these gray lines, this is the type of world we would live in. We will never live in the mean. We're going to live in one of these trajectories. So we might live in member number 40, or we might live in member number, say, 32. And the type of work our group does when we think about these different trajectories or ensemble members is we use AI to leverage these imperfect climate models to constrain future projections. And really, the idea is that we're using it to understand either the global warming signal, that is that long-term trend, the forced response, but we're also using it to do day-to-year climate prediction. That is, if we lived in world number 32, would we be able to predict ahead of time this cooling that is seen from 2020, say, to 2050? So multi-year predictability. This has important implications. So climate prediction is important, obviously, to prepare for weather and climate hazards, but it has a secondary importance that I think should really be talked about more, which is as we think about any sort of climate action and policy, anticipating the potential masking of intended effects of climate policies due to internal variability may also be a really important reason for us to be able to make predictions. That is, if we're able to make the predictions ahead of time, El Nino is we have an extra strong El Nino coming up, for example, will that help with when certain climate policies maybe are blamed for working too well or not working at all, et cetera. All right, we're also doing work on even shorter time scales. So thinking about subseasonal to seasonal. So making prediction days to weeks in advance. I'm going to tell you a little bit about some of this work. But first, I want to point out that it's really easy to make little diagrams like I just showed you, but climate prediction is incredibly challenging. People have been working on this for many decades. So I am not going to come in here and tell you that we can make perfect predictions all of the time. Hold on, sorry. There we go. Okay. In fact, we frame this instead by looking for specific states of the Earth system or forecast of opportunity that lead to enhanced predictable behavior. And when you frame it this way, you hopefully can see that something like a data-driven approach like AI can help with this. I often think of it as, imagine we have some 2D data here, and 80% of the data is just a blob of noise. But we know that sometimes there's a signal, and when that signal is there, it's useful. So say 20% of the data signal, and we really shouldn't be trying to average everything together, but we're really looking for that signal in the noise. And so AI is useful for that, but more importantly, it means we have to maybe take a different training strategy, since impossible predictions may be hampering AI learning of predictable behavior. Now, this is just a toy example, but in reality, in the climate system, we do in fact have sources of predictability that act in this way. For example, on 30-day timescales, we have something called the Madden-Julian oscillation, which is sort of band or group of tropical convection that moves from west to east. And when it's active, can lead to predictable signals in the mid latitudes. Or I've already mentioned this, but the El Nino Southern Oscillation, which also has implications for weather worldwide. So when these phenomena are active, perhaps then we have predictable signals. So in fact, we have quite a few studies where we try to leverage this state-dependent predictability or this forecast of opportunity and find them with AI approaches. I'll give you an example here. So this is work by Frances Davenport, and what she did is she trained a neural network to take in past sea surface temperature information, again, looking in the past to try to get some information about temperature tendencies or time changes, and predict in the future whether the sea surface temperatures would be warm, average, or cold in that region. So we're thinking here about 0 to 5 year timescales, so much longer than a typical weather timescale. So first, she trained on climate model data. So this is trained on 3,630 years of data, which is a lot. And the overall accuracy of predicting SSTs in this way is shown in this map here. Now, the way it was trained, it's a 3-part classification problem. And so random chance is a third, and that's yellow. And if you look at this map, it looks pretty darn yellow. So at first you might think we have absolutely no skill. Our overall accuracy is about random chance. And this is true. This is what that map looks like. But if we instead try to leverage when the network is most confident in its predictions, which I'm not talking about how we do that here, but I'm happy to take it during Q&A. If we look at when the network is most confident, that is when it thinks it has skillful forecasts of opportunity, we actually find that we do have skill much better, well, better, I won't say much, but better than random chance in specific regions of the globe. And if we take predictions that are even more confident, we find that for the most confident predictions by the network, that is when the network has identified a forecast of opportunity, indeed, we do have high accuracy. Now, this is just for a climate model, but when we take that same network that was trained on the climate model output and we apply it to observations, we get a similar picture. If we looked at overall accuracy, it would just be random chance. But if we only look at the accuracy when the network has identified a forecast of opportunity, we actually find skill that exceeds random chance and actually has information in it. Again, we've made these predictions, but now we'd like to learn why the network is making the prediction that it is. Specifically, XAI can help us identify the sources of predictability and why and when the network is declaring this forecast of opportunity. So same idea, taking a network that was trained on sea surface temperatures to predict, in this case, land surface temperatures in the coming 5 years. And then we're going to use this attribution heat map approach to make maps of the most relevant regions for these forecasts of opportunity. And those heat maps look like this. Now, this is not a cat in this case. This is a heat map showing the most relevant regions that the network is using. So when making predictions in different locations on the globe, shown by the red dots, the network has identified different regions of sea surface temperatures that are important for those predictions. For example, for Mexico, the Kuroshio extension, over the Midwest using ENSO, and over Canada using information from the Atlantic. But on top of this, because these AI models are nonlinear, they are able to identify different sources of predictability, even for the same location, depending on the climate state. So this is for a prediction, for predicting, temperatures on the west coast of the US, and the network identifies different sources of predictability for the same prediction. All right, so this is work that we have done on the large-scale climate prediction space, but largely it's been based on standard neural networks, that many of us have become quite used to. But as I mentioned at the beginning of this talk, AI emulators, that's fully AI data-driven models of the Earth system have appeared. And I would argue that one of the reasons or one of the ways we can start to learn new science from these approaches is we need to start to think about new experiments, not just doing the same ones we've been doing, but faster, which is still useful, don't get me wrong. That is, AI emulators, as an example, are going to let us simulate thousands of possible hurricane seasons and not just forecast the next one. As an example of some of this work, we're using a particular AI emulator called ACE2. I'm happy to chat more about specifics in the Q&A. And because it is inexpensive, but also can capture the dynamics of tropical cyclones at a fraction of the cost of our physics-based models, we can actually start to think about the probabilities of certain hurricane seasons having happened and put probabilities to how likely they were given internal variability. So in this case, this is highlighting the fact that the 2020 hurricane season was relatively anomalous, very active, and using this emulator approach gives it a 0.5% chance of happening due to atmospheric noise and internal variability. Now, again, because we can simulate tropical cyclones in these emulators, we've actually been able to use them to look at hurricanes and typhoons over the past 500 years. So in this case, this is focused on the 1600s. We have work focused on the 1600s. Specifically, Muting in my group has been using and corroborating handwritten records of typhoon impact on eastern China, which is just amazing these records exist. And finding, and as others have found, this is not her data set, but collaborators, finding this peak in activity in the 1600s. And one question was, why did this peak happen? So what we were able to do is leverage proxy records of sea surface temperatures over the Pacific during this time and push them into our AI emulator to actually try to simulate this same time period. And in fact, the AI emulator can create multiple trajectories that appear quite similar to the peak that we see in the handwritten records. What's neat is now we can start to study why might this peak have occurred. But in fact, first, our physics-based models, and I should say our physics-based models also show a peak. However, we can only do one simulation with our physics-based models because of the resolution required to simulate typhoons. And so the AI emulator allows us to run hundreds, if not thousands, of members, whereas the physics-based model only allowed us to run one. What's interesting further about this time period, so Muting's been looking into why this occurred. One is this was a particular this was the solar minimum, and we do think that had an influence on the sea surface temperatures at the time, as well as El Nino-like conditions over the period. And so she's currently using this emulator to try to understand the reason for this peak in hurricanes in the 1600s. All right, so these AI emulators like ACE2, and there are many, many others, many weather emulators as well, allow us to forecast sort of thinking into the future and make long time series of the statistics of climate. They do this typically by what's called an autoregressive rollout. So they all tend to, most of them, share this underlying principle of saying, given the state of the atmosphere at T0, how do we expect the atmosphere to evolve at T0 plus delta T, where delta T is typically 6 hours. And then the network outputs the answer, what the fields will look like 6 hours later, and you put those back into the same network to predict the next 6 hours. And in many ways, these work like the time stepping in our physics-based models. So the goal, again, is with these AI models to optimize these parameters to get a better prediction at delta T or at 6 hours. However, there are a few new ways of approaching emulation that are just coming out in the last year or so. And C-Bottle is one example that's out of NVIDIA. And it's generating weather states, don't think of it as rollout forecasts. This is called climate in a bottle. What they do is instead of this autoregressive approach, which I just showed you, the model takes in the day of the year, the time of day you're predicting for, or you're simulating, I should say, monthly sea surface temperatures, so boundary conditions, and the data set that you're training on or using, and it generates a plausible atmospheric state given these conditions. And furthermore, it has a video version where you can do this for a set of time steps simultaneously. So you could put another way, what you say is, I want to know what a world could look like on January 2nd at noon, given these sea surface temperatures. And it will give you a video of a 66-hour video of what a climate state could look like. If you do that many, many times, you can start to make and understand the statistics of that particular climate state. So that is one approach that is starting to be studied more, but in our group, we're actually using this to do something very different than we've been able to do with physics-based models to date. That is, we're going to start conditioning not at the beginning, but on the end. Put another way, imagine that instead of thinking about where you're starting or the world you want to simulate, you think about the world or the event you want to end at. And you start to ask questions like, given I'm here today, and given, say, I want to simulate a hurricane hitting the East Coast in 3 days, tell me what's going to happen in the middle. And that's, in fact, what we're doing. So this is work by Jerry Lin, a postdoc in my group. He's feeding this model the condition he wants to start at. For example, a hurricane here in the south of the US. And then he's saying, I want it to end at landfall, say, over Florida. And we're using this generative approach to then connect these two and simulate or interpolate the fields in between. So something like this. So connecting that beginning state with the end state. And this is what I meant at the beginning of my talk, where I said, I think we need to start developing new experiments. This is not something you could do with a physics-based model. Now, furthermore, what this means we can do is we can steer trajectories for the use of extremes planning. So this is not a forecast, but we can use it to actually understand and make scenarios for planning purposes. For example, here, starting the simulation in exactly the same place, but having it end in different locations and connecting those two in a plausible, physically plausible way. As an example, we've done this now for 1,000 different ways, for example, that Hurricane Sandy could have made landfall, and it's allowing us to think through these different scenarios where, if you will, the observations is just one of them. All right, so these experiments depend on emulators faithfully representing the physics, and we're still figuring out if they're doing that. Furthermore, AI models can struggle with events outside their training distribution. So predictions and simulations tell us what the model can do. And again, these are still early days for that. But our group is now starting to go further and ask about training. Specifically, training tells us how it thinks. And that is to contrast this with the first part of my talk, maybe we don't have to open the black box after the fact. Maybe instead we should be watching it built from the beginning. That is, we should be watching it during the training process rather than trying to explain the final end result. In fact, there's more appreciation for this coming out. This is just a recent paper from last month, that the emerging theory will be concerned of AI will be concerned with the dynamics of the training process. Furthermore, and we're not here yet, but I see this as really exciting work because for the LLM space, they're starting to follow and watch LLMs train in hopes that there are specific training moments that are particularly important and they can be manipulated to improve the final result. And this is, in fact, what we're trying to do for AI weather and climate models. So just to give you a sort of a sneak peek of some of the results we're finding, here's how this works. So we're turning the training process into an experiment. That is, every checkpoint you can think of as every epoch, we are saving the network's weights at that point and watching it train. Now, once the network is trained, we have all of these checkpoints, including the final network, saved. And we're going to use all of those different checkpoints or versions of the network to make the same exact forecast over and over again. And we're going to watch it hopefully improve on that forecast as it learns. So here's an example from Annabelle Wade, a PhD student in my group. We're going to task the network. In this case, we're going to use ForecastNet version 2 out of NVIDIA to predict this atmospheric river event 7 days ahead. So this is the target. This is what we're having it predict. So after checkpoint 1, the network has already predicted that the network, that the AR is about in the right spot, which is honestly very impressive. This is not a cherry picked example. This was the first one Annabelle did, but this was pretty impressive. By checkpoint 3, the network has made the AR wider, but it's moved it else, off axes. We can keep going. Checkpoint 5, the network's getting a little bit better, a little bit better, a little bit better. And by checkpoint 15, the network's forecast is starting to look pretty good. So let's keep going. At checkpoint 23, checkpoint 25, now the network's already, its forecast is looking excellent. So what happens next? If we keep going, we actually see that the network forgets how to forecast this event. That is, between checkpoint 25 and 27, there's what they sometimes call catastrophic forgetting on this particular event. And the network has to relearn how to predict this atmospheric river all over again. And in fact, it does do that. The model does ultimately relearn to forecast the event. But if we'd only looked at the final model, we'd never know that this had happened. Now, the fact that it ultimately predicts the final event might suggest, well, who cares? It forgot it and it relearned it. What's the big deal? Well, some other work by Becca Bayman in my group is suggesting, in this case, not looking at atmospheric rivers, but looking at tropical cyclones, that there is a large suite of tropical cyclones the model forgets and then never recovers learning. That is, the network was good at predicting these events early in the training process, and then over time got worse and worse until the final network was unable to forecast these events. Right. Okay, and one of the things we're finding, there's lots of details on here, and given the time, I might start to wrap up. What we're actually finding is that it's about a third of the tropical cyclones in the Atlantic that the network does a good job of training on early on. So a good job of forecasting for early checkpoints, and then and then unlearns and fails to recover at the end. A third of these tropical cyclones is not just a cherry-picked example, but it's a large fraction of the types of extreme events we care about. And something Becca is just starting to realize or discover is that there's something common about these unlearned storms. Specifically, they're storms that are acting in very moist environments. So we are finding that the network is somehow being confused or unlearning the moisture relationship between moisture and intensification. And we're still digging into why that step is. So every time we dig, we get more questions. So the whole idea here is that training dynamics can reveal how AI models think. And the hope is, where our work group is going, is it will help us identify when to intervene in the training process to do better at things like tropical cyclones. So we're finding this for multiple types of extreme events where they learn, forget, and sometimes recover. We're actually finding these sorts of behavior are true for both weather and climate emulators. And we're currently investigating the latent representation within these AI models. So what the models are encoding and how it's changing through training, as well as trying to use this approach to figure out when the networks are learning physics. So the whole idea is, watching it learn, locating where that learning is happening and how, and then hopefully intervening to make the models better. And so wrapping up here, just in terms of what's coming next for the community, there's a lot going on. I don't mean in any way to say that's only 3 bullets worth, but a few things that might be of interest. First of all, most of the AI emulators I've talked about were atmosphere-only models, so they needed to be forced with boundary conditions of the ocean. But in fact, fully coupled, so that means atmosphere and ocean coupled models are coming online now. So there's one model here I'm showing, Samudrace, that is already out. There are tweaks that are being done, but I think there may be less need to prescribe ocean temperatures in the future. Also, AI native downscaling, this is an area that's gotten a lot of interest, is taking coarse-grained features and downscaling them for regional impacts. But one note I want to point out is that the pace of the development of these AI emulators is certainly outrunning the community evaluation. So I just want to point out careful validation is more important than ever. And just because somebody has output an AI emulator, which actually these days isn't that hard to train and to do, the validation and verification step is a long process. So just to finish here, emulators, I will point out, are trained on non-stationary reanalysis data that doesn't exist for the climate we're in today. And so what does this mean for how we use them and how we assess their statistics and probabilities that they're forecasting, I think remains an open question. They can generate thousands of plausible futures in minutes, enabling us to characterize risk at high resolution quickly. I suppose this is not so much a challenge, but something that is exciting and worthy of exploration. And then finally, interpretability methods that work for things like CNNs don't necessarily work for other types of models. And so we need new approaches. And I would like to argue that watching them learn could potentially be a major new way forward. Another benefit of watching them learn, I would argue, is that as long as you save the checkpoints during the training process, which isn't typically a huge, storage ask, you can do a lot of science later with those checkpoints. And so with that, I will thank you and take any questions until an alarm goes off.
Thank you, Libby. Great talk. Let me do the virtual clapping here. Okay. So are there any questions from the audience?
That was a really great talk. Thank you. So you framed explainability as a step towards causality, and I've taken a lot of interest over the years in sort of the gaps between what explainability wants to tell us and the real mechanisms of the models. So have you considered causal methods such as causal discovery or other causal explainability approaches?
The answer is yes, I've considered them, but we haven't implemented them. I know there is a small but hopefully growing amount of work about causality and AI, and networks together. It makes sense. We have worked with causality approaches for climate previously, but not with networks. I think that's personally an incredibly exciting way forward. So if you're working on that, great. For us, I would argue we're still using that step between explainability and causality is still really involving the human to sit there with all their domain knowledge and draw those connections. So if anything, the explainability part is really more hypothesis generation, which then we would go maybe even back into a physics-based model to test. So we're still early days as a group, but I think it sounds like folks like yourself and I know of other colleagues that are making much better headroads on that.
Makes a lot of sense. Thank you.
Yep.
So I see Randy Brost has his hand up.
Yeah. Hey, thank you for a fascinating presentation. My question is very closely related to the previous question, which has to do with causality. I really appreciated the, I'll call it backpropagation, but it's not exactly backpropagation, where you were able to show the regions of the Earth that influenced weather at a particular moment of time for a particular target location, like say California or Mexico. That was very interesting. And that left me wondering, okay, well, that's really interesting information. The question was why? What is the connection? And that gets into the causality issue that was just asked a moment ago. But I guess my question would be whether you can speak to the causality in some of those instances, or maybe speak to your understanding of our current ability to fill in that gap using the manual methods you just described.
Yeah, so actually, thank you for that. The manual methods I actually think are largely tried and true. Like we've been doing this for decades, and we have a lot of different theory, physics-based models that we've tried to test out our causality ideas or look for physical mechanisms. Mm-hmm. And so this is typically when I give these talks to sort of earth scientists, I say, this is where all your training really comes in, right? Now, the extent to which that can be done has to do with past work, et cetera. Let me just give you an example, because I realized that was very vague in general. We did some work like this where we identified a certain region of the Pacific Ocean as important for precipitation hitting the west coast of the US. And then what we did is we actually took that one region and we forced a physics-based Earth system model with temperature tendencies only in that region to see if we actually, in fact, got the signal that was learned by the network. In that case, it worked beautifully. And just gave us this, the full circle scientific process, if you will. Now, if you want to go even deeper and say, well, how is the ocean of the Pacific influencing precipitation? That's where we start to rely on things like our understanding of deep convection, thermodynamics, Rossby wave propagation, et cetera. So I think in that scenario, that's where that comes in. I would love, when I give talks like this, oftentimes people will come at me and be like, well, the AI didn't actually tell you the physics. You had to sit there and figure it out. And the answer is so far, yes, this is true. I think there's a possibility of having it do more, but I think we're still figuring out what it's learning in the first place.
Well, thank you for that answer. I think it's a fascinating answer, and I don't want to monopolize the question, but I'll just make one observation that,
yeah, please.
From some of the early days of robot vision-based navigation, there was a notion of an interest operator, and this reminds me of that, where the predictions of those relationships then create a question to which you can apply a more detailed analysis. And that was a very effective technique in that completely unrelated domain, and I'm just reminded of it now. So that's a very, very interesting answer. Thank you.
That was great. Thanks.
Yeah, I guess I'll make a question or make a comment or ask it's a little bit of a question, but yeah, I'm surprised you have enough data to train these things, because usually for climatological data, it's the number of ensembles, even if you consider these MIP studies and different climate models, it's pretty limited. I guess it's because it was atmosphere only that you had enough data. Is that because I could imagine that will be an issue when you go fully coupled?
So I think you're referring probably to the emulators in that case. So the second part of the talk. Yes. Yeah. So when these weather emulators started coming out like 2022 or so, everybody's like, oh, this is, especially the folks that were not earth scientists started saying weather's first, but then we're going to do everything. And of course, it's all about time scale here and independent information. If you're trying to predict 6 hours or 6 days out, we actually have quite a bit of independent information that is largely reliable going back many decades. But that same many decades only has a few independent samples when you think about variability like the El Nino Southern Oscillation, which has a time scale of 3 years or 2 years, which means you really only have a few samples over those few decades. That is something that I think as a climate community, we are very aware of, but many from like the AI side, I'm watching them realize that. Even 2 years ago, I would have so many calls with startups that they were going to sort of solve the sub-seasonal to seasonal prediction problem. And I kept asking, where are you going to get the data? And now, of course, we're seeing that it hasn't been some explosion of skill in that space because this data doesn't exist, or the amount of data we need. However, and this is something I've been saying for a long time now, I do think this is why things like fine tuning on observations, but training on synthetic climate model data is key to the way forward for timescales beyond weather. How we do that, in this case, in this talk, I showed you examples where we train on climate model data, and I sort of joke, we cross our fingers and just hope it works on observations. I also showed you a simple example where we trained on climate model data and fine-tuned on the limited observations we had. I think those approaches are going to have to become much more sophisticated to really make use of the synthetic data we have, but not also repeat all the biases.
Yeah, okay. Well, thank you. So I see Jennifer Page has a question in the chat. Jennifer, do you want to unmute yourself and ask the question?
Yeah, sure. Thank you so much for this talk. It was really interesting. If I can just ask maybe a more basic question, but when we talk about causality, would you mind just defining like what it would mean to do causality, and if it's trying to understand if the AI is learning the physics and then what physics is creating the weather/climate you see, or what exactly you mean by causality?
When I'm talking about causality, I actually mean in these past conversations, I actually mean the real physics of the Earth, not so much the causality within the network. I think that potentially, I'm not going to say easier, and then I'm going to have to run. I've just been told I'm doing 15 flights of stairs. So that, not easier, but we can actually, I think, have ways to probe that in these AI models. The question more is, first, is it learning reality? And then even if it is that a causal link or merely a correlative link that still gives us the prediction that we wanted?
So it's a separate question about like what physics is causing the weather or climate that you see?
Well, that's also a physics model too.
Okay.
Correct. So it's multiple layers.
Okay.
Yeah.
Thank you so much.
Yeah.
And good luck with the stairs.
Yeah, thank you. Okay.
Any last questions before we let Libby run down 15 flights of stairs? All right. Well, yeah, this
thank
was an
you.
excellent talk. I think you set a new record, and we had like 70 people in the middle
Oh,
here.
hooray.
Yeah,
Thank you
so
all for coming.
I think it speaks to the level of interest in your work. Thank you very much.